Good. Coming back to our random number generators. There was a time in the beginning with network coding where we had the feedback, it's a nice concept, but it's not working. And we were at the stage that, yeah, it's working, it's not efficient, it's not speedy, but it works. But they claimed it's not working. They got values for linear dependencies, I've never seen them, right? Until we asked them, on which operating system are you working? And they used Windows, we used Linux. And then we asked, which random number generator are you doing? And the one that is in Windows. And if you know something about security, Windows has an extra library for random numbers for security. Because they know the normal random number generator is crap. So there seems to be good randomness and bad randomness, right? So the one thing that we found is this nice Dilbert, right? Where Dilbert, he is an engineer, and then he was introduced to the new number generator that they have in the basement, right? And by spawning it, the random number just said 9999999. And Dilbert just asked, is this random? And the other guy said, yeah, you never can say. Could happen, right? Yes. But it seems to be not a very good number generator, right? Depending out of the elements he was getting out. So we looked a little bit into this random number generators, right? You need them for simulation, for cryptography, gaming, but for our coding was even ours. And then there's deterministic versus non-deterministic. So what you could do is, and I remember that in the early days, we just had, in the PCs, we had a radio, an FM receiver. If you put it on a frequency where there's only white noise, you can just take the numbers from there, right? Then you have only the latency of the API. So atmospheric noise, thermal noise, AM, FM was good, quantum phenomena. So this is something measuring. And then you have something that looks random, right? And these are called pseudo-random number generator. Or you could even derive this from a random number generation from a probability distribution. That's also possible. So we will look more into the pseudo-random number generators. And I don't know if you know how to do it, but if you have a generator, there's some quality in it, right? So when we have a sequence of random numbers, R1, R2, R3, the question is, what is a good random number? And there are two things, uniformity. So we say if there's an interval between 0 and 1, where 0 is an element of the group and 1 not, and we have n observation, and we divide it into n subspaces, then in all of these subspaces we have n over n elements. So there should be not having a certain tendency to one or the other. Then the independence is that if you have one in one of the observation fields, you cannot predict that if you have something here, the next one it will most likely to go to the other group. Therefore, it should be independent where they're falling. And the properties then is, okay, how fast that is. Yeah, for Codo wants to have a very fast random number generator. Then we also would like to bring it to any platform. We are on Intel, but we're also on AMD. We're on Linux, we're on Windows, right? That must be portable. We want to have a long cycle. Long cycle means they should not repeat after a while. You will see that pseudo-noise random generators, they come up with a sequence, and after a while it repeats. And if we would repeat it, it would be great if we get the same random numbers. So if we have a starting point, the so-called seed, you always get the same. Why is this so important? Because then you can really, if you find a certain situation, you can repeat the situation. You can train your system towards this. This is quite an interesting point. And maybe you can look it up if Codo still has the seed encoder decoder. Is it still in the new version?
I didn't check it.
Yeah. You can check it now and tell me. The thing was, the encoding vector means I'm telling always the random numbers. But if I have this function of repairability, why do I have to convey my random numbers to the other side? If I send it to you, and just you, then I could say, okay, I took this seed, and this is my random number generator. If you understand that, I just pass you the seed once, and then coding vector is gone. You know what I will do, which coding coefficients I will take out. Now, coming to security, that is not really good, right? And the other thing is, we can only do it point to point, or point to multi-point. Because if you start to recode these packets, then there's no way to understand what we're doing by recoding, what we do to the seed. We talked to a mathematician and said, can we recode and you tell me which seed I should say in the end? They said it's impossible, right? But they knew the problem. They knew that there is this problem because it's a function of a function and you convolute them. They understood it, and they normally need 7 years to come up with a paper on this. Maybe there will be something. But interesting is the fact, if I know a seed, then I just convey the seed and the encoding vector is totally gone, right? So every time we come to this little overhead of the encoding vector, this is one way to get rid of it totally. Sparsity, you can compress it, all these nice tricks, but this is one to get them really down. Okay, and then this ideal uniformity and independence that I told you before. So I tell you now some methods, right? How these random number generators, where they're coming from. One is called the linear congruential method, LCMM, by Lehmer in 1951. And he will produce random numbers, x1, x2, x3, between 0 and m-1. Later we want values between 0 and something smaller than 1. Then we divide just by m, right? That's what we're doing here. So, and how do we do this? There's only one operation. We say, okay, my new random number is my old random number multiplied by a plus c mod m. And then you say, x0 is the seed, what I told you before. This is the initial start. And a is just a multiplier, c is an increment, and if c is equal to 0, we call it a multiplicative congruential method, otherwise it's mixed congruential method. And m is the modulus, right? And there's the paper, 1949 to 1951, right? This is submission and publication, I guess. So, and now, as we said, we would like to have numbers that are smaller than 1. Then we just take the integer values and just divide it by m. Okay? That's quite easy. And the properties of all these R then depends heavily on the selection of these 4 parameters. And there's some good selections and some bad selections. And you go to notebook Deutsche Telekom Rocks. Just open it. I want to see something there. So what we do now, we say, okay, let's do x0 is 27, a is 17, c is 43, m is 100. And then x0 is 27 by definition. x1 is then the 17, the multiplicative thing here, by the old value x0 plus 43 modulo 10, this is 2. So my first random number is 0.02. And then I continue. I take the value 2 here, 17 plus 43, 177. So my new random number is .77, which means you see already as we have 100, it becomes very easy. So if you continue here, and I gave you already the color, once you have the fourth number, 27, you take 27, multiply it by 17, plus 43, modulo 100 gives you 2. And then the 2 you had already. And if you continue, you'll find out the next one is 77, 52, and so on. So now we see we get 4 random numbers, and then it continues. Then it repeats itself. And then it repeats itself. And the average element of the list is .39. Not very good, right? So we expect a random number between 0.5. But because we are just throwing 4 numbers, it's not very good. So what can you do about it? In order to produce these plots, there is a Python script for that, if you want to have it. It should be also on the notepad. Is there? So you see here the Python script, and it exactly gives out the numbers that we have seen before. So what you see here is actually getting out of the Python script, because I was too lazy to do it manually, right? But you can test it out on the Python script yourself and play around with this. Now, we have the Python script, and we have something, we have seen that we have get this lousy. Can we improve it? That's the question, right? By the way, this is the more advanced one. I have also done a very simple one, just to show you this. This was the initialization value. Here you create one list, and the first thing that you will append to the list is x0, so the seed was 27. And then you said, okay, for a certain range, right, at least m plus 5, we said, okay, go there, calculate a, take the last element of your list, plus c modulo m, and then print the list. That's the easiest what I could program for you. The other one I need later for something else. But this is the easiest way to create a list of random numbers. Now, what we had now it was not so good. What we're looking for is maximum period and a maximum density, right? So how can we make it larger? And we said it heavily depends on the initial values that we choose. So what are good values to choose? What is a good A? What is a good x0? And there are some people that thought about it, and then in 2007, so just to tell you how research works, right? More than 50 years later, there was this law paper. He said it has been shown that the maximum period, and he also proved that, can be achieved by the proper values. What are proper? So we will get a period of exactly m. M was 100, right? So we only got 4, but he promised us exactly m equal to 100. If m is power of 2, this means m equal 2 to the b, and c cannot be 0. That's the only thing. That means non-zero, right? And if c is relatively prime to m, so this means the greatest common factor of c and m is 1, and a becomes 1 plus 4k, k can be any integer, then you get the maximum period out of it. So let's try this. M equal 2 to b, so in this case, for example, equal to 2 to the 4 equal to 16. So I don't take 100 because I don't have this, right? But just to give the point. C is non-zero, check. And A is 1 plus 4k, so let's take k for 4. 1 plus 4 by 4 is 17. Okay, then we do it. So you take this out, and you calculate all the values, and I spare you the details. I just tell you, you can go in until you get element number 16, and by 17, it's restarting, and then 18 is the 2 and so on. So now we have exactly m elements by choosing it correctly. Now the average element of the list is 0.51. That's quite good, right? 100 numbers, 16 numbers now out of between 0 and 1. That's already better. And of course, if you go back and make these examples bigger, you get better numbers. I tend to keep them small to be able to just print the output here with you, okay? I think everybody is clear. If you would say b equal to 10 alone would do the job. Okay, now the question is, what happens? And there were other proofs. I just gave you the best, right? If you learn this, everything is fine. The paper had some other nice proof that I just don't want to hide. He said the period now equals a quarter of m, so 2 to b minus 2, if m is the power of 2, they had this before, and c equals 0. So this shows you the importance of this non-zero. And a is 3 plus 8k. So now we say, okay, let's be z is 0. We take here a new number, whatever. The seed is still the same. And then you see, if you put it in, now m was 32. We said the period will be a quarter of 32, and you get 8 elements, and then it will repeat. And the average element is a little bit worse. So why I'm telling you this? I told you the better one before. I could even hide this and say, take the other one, best. There must be a reason why I'm telling this. So, if you look at this, the only thing you do is A multiply reading out of an element plus C modulo M. The only thing that is more or less changed from the complexity point of view is C is 0 now. So you will not do one addition. And what does it mean? Speed. It's just an addition, you might say, right? It's one addition. But if you talk to the people who also implemented the code library, they are even furious to have an if element there. So this could be something where you say, okay, if we only get a quarter of m, fine, right? As I said it. Here we get only a quarter of m. Then I make m very large, but I don't have to do this addition. And if you have to do one addition, it's not a problem. If you do millions of additions, that takes time. And normally you do a lot of these operations. So I'm telling you this, if you think about speed, it looks not as nice because there's only a quarter of the maximal period, but there's one addition less. And this one I showed you already. I can even say, wait a minute. Did we say something about the initial value? Here, there was x0 has to be odd. That was the only thing I did not tell you. We had, it's 27, so therefore I wasn't thinking about it. Just to show you what happens if x0 is not odd, then here you had 8. If you now make the seed 26, then you don't get the 8 elements, you only get 4. So it's not the best you can get out of it, okay? So therefore, you have to choose these things wisely. Okay, anything else? He could even show something else. He could, the same paper again, right? I think he was on fire. While 60 years nothing happened, he said another one. So the period equals m minus 1, so very close to the m. If m is prime, any prime, c is 0 if it has the property that the smallest integer k such that a to the power of k minus 1 is divisible by m. And this is k equals m minus 1h. 1h. Now I even have to figure this out. Let me find it out. So let's try. M should be a prime number. So this is optimal prime thingy again. 2 to the power of 5 minus 1 is 31. Okay. So there should be a period of 30. C equal to 0, easy. A is, if k is 4, this means no, wait a minute. K smaller. Okay. A is 17, so is divided by m is x0. Is this correct here? 1h. I think there's something wrong. M1K. I have to look this up. Not totally sure about this last element here. Good. Nevertheless, let's take this and let it run through. This is a 17. Okay. If you start like this, you get exactly your 30 elements, as we said. And now if you look, even here, you don't have any addition to do, right? And the average element is 0.52, also good. Something went wrong here with the conversion, I think. So let me just have a look at if A has the property that the smallest. Okay. This is wrong. I think the H is wrong. K is equals M minus 1, 30. A 17 to, so that we have to prove if this is correct then. I'm not doing it now, but let me at least informed that we will get a very long period if we have M, which is a prime number 2 to the B minus 1, right? And then we check it out later what this means down here. Okay, now can we do even some other thing with this? For the numbers here, for the prime numbers, you can even go up to 2 to the 31 minus 1 is a Mercian prime number, right? We did something similar with 2 to the 32 minus 5, right? Some specific prime numbers. And then they found out what the best K is for this, which is 16,807. This was already known from 1969. And then there are other options to do that. So this comes from 1988. So these Mercian prime numbers, they are also very interesting for doing the prime numbers here. So if you are not happy with the result, what you can do with these LCM generators, and you say that you have a large period, but this is not enough, how can I go larger than this, right? And then you can say, okay, I'm combining them. So what they are doing is, let's take 2 generators. The one has A1 and an A2, there's no C. And then you have M1, M2. They're more or less the same. They only differ in the last 3 digits. Okay? Then you can select 2 seeds between 1 and exactly the amount of M minus 1, so M1 minus 1, and here between 1 and M2 minus 1. So if you follow up this, then you can say, okay, you loop. You just say, okay, I make a new value in my first generator and a new value in my second generator, which is done exactly as I told you before, right? This is the M, these are the A's, and then you subtract them from each other, right? And then you modulo by one of them, right? And which one you should take? The maximum, of course. The maximum of the stuff that you choose here. So max M1, M2. And then you get random numbers, right? Which is the new element divided by this, or by if the outcome is larger than 0, you have to divide the outcome by this number, or if it's equal to 0, if the new one is exactly 0, then you have to do this equation, which is M1, so the maximum, also in this case, minus 1 divided by M. Okay, I did not make any program for that, right? I think you can do this, but now the combined generator has a new period of exactly the 2 periods multiplied, more or less, which is then 2 to the power of 10 to the 18, which is quite good. I mean, this is very long. Normally you don't need this, but just who knows, right? Who knows? And here you can now try to do it yourself. I think we have done that. Here you see the initial values and the initial seeds. Then we had the M values. We found out what is the maximum of these two values, -1. Then we took some A values and then the C values. Why did we, C? He did not use C, right? Did we use C here later? We used it here. I would set this to 0. I think it will not harm to put their value, but for the complexity reasons, just put it to 0, right? Actually, don't put it to 0, take it out of the, because even multiplying a 0 will maybe take away some of your stuff. And here you see how we create the list, and then we print the last list. Good. Are there any ways to make a random generator that is maybe easier or less complex? There's a Tolsworthy generator. Just to show what it is, it's very quick and it can make very long random numbers, right? This is produced on a stream of bits and not on numbers. And I will show you how this works. And this is from 1965. It just says we have here a sequence out of a combination of bits. And we only need exclusive ORs, which are pretty fast on the calculus. So before I explain you this one here, there's the characteristic polynomial. You have a primitive polynomial to do that. Then you just have to say, okay, I have here my equations, and then I just use the primitive polynomial to calculate something out. But if you want to, for a starting phase, for example, you say everybody, we have 7 bits, I set them to 1, and then I calculate what is B7. B7 is B3 multiplied B1 is 1 by 1, this is 0 in XOR terminology. Then you say, what is B8? It's B4 by B1, this 1 by is also 0, and so on and so on. This is very easy, but graphically you can even look at it like this. So you get something like this, you have some bits, and in order to calculate the bit number 7, you just go here, get an XOR, and you write the value here. Once you have done it, you move it to the left. And so on, you always move it up, and this is very quick, right, as you can see. There are even better ways to do this than just moving it like this, but I will not tell you about this, just that you have the understanding of it. The interesting part is, if you want to map this to the other generators, this is your, not this, B0 to B6, this is your seed. Okay? And this is a construction of the randomness. Right? In this case, where does it come from? This is the thing that tells us the new B is go back 4 bits, go back 7 bits. That's the construction. And this depends on the primitive polynomial that you are using to do that. So quite simple. Also here, writing a script for that is not very complicated. We only made it in a straightforward version. If you use some functions, it's easier, but here you understand how it is, and you can print out whatever you want. This is now the result for the first 150 bits. What's coming out here? So why I'm doing this, I took now this initial sequence of ones, because if you go through it and you look at it, oh, here are also a lot of ones. And after this, so I'm looking where does it restart. So what is the period now? And you see, after a certain time, it's also repeating, right? And this is exactly after 127 elements, and this is given by the primitive polynomial, right? It's 2 to the 7. Good. Now, if we know this random number generators, you don't have to program yourself. Sometimes you have to do it for very low-cost devices where maybe nothing is there. We looked into different random number generators, right, on different machines, and this unit x is how many x bits you generate at the given time. And even though they are more or less the same platforms, different generators help you to get numbers quicker or not. This will have an impact on the performance, right? This was for unit 8, this is for unit 16, right? And if you read this, right? This is the one that we used before. So they are based on different mechanisms here. Okay, this is for unit 32, so different baselines, not so interesting. 64, not so important. Yeah.